So our goal for today in 6.1 in Introduction to Probabilities, we're going to calculate probabilities for events in which sample space is small. A drawer contains 7 red socks, 8 blue socks, and 12 white socks. Assume that you draw a sock randomly from the drawer. You close your eyes, it's perfectly dark, something like that, and you are trying to pull a sock out of the drawer. Just to recall fundamentally, what you're looking for is when you're looking for the probability of an event occurring, and we'll unpack this a little bit further. So this means probability of event. What we're looking for is the number of favorable, that is what I want, over the total number of options. The number of possible, the favorable over the possible. That is what I want compared to what the universe could give you. And I say that in the non-offensive use of the word universe.
What's the offensive way?
All right, so what is the probability that it is red? Well, let's see. So this is how we write it. The probability of red, we would say this. The probability of red. And inside we put the word red. And we say equals. What we do is we count how many red we have. And as we see, we have 7. And then we count the total options we have. 7 plus 8 plus 12. So that's 27 total. So this is my probability, 7 out of 27. And of course, we can approximate that to be a decimal. 0.259. Another way to say that is 25.9%. So not white would be the other two colors added together. And 15 over 27 clearly is more than 0.5%. So in the end here, 0.556, which is also equivalent to approximately 55.6%. Zero probability that it's green. Now, of course, this is also based on the fact, the assurance that you know there's no green in there. All right, so let's walk through some of our general topics and definitions that we have regarding probability. So the first part, the outcome and sample space of an experiment. So first off, an experiment is any situation that can have multiple outcomes. Flipping a coin, rolling a dice, spinning a spinner, randomly selecting a person, something like that. Probabilities are measures of how relatively frequent the results occur. Does it happen often, like 6 out of 7 times? Does it happen infrequent, like 1 out of 7? So, in each result is called an outcome. Each result is called an outcome. The set of all possible outcomes is called a sample space. So let's walk through a few examples of sample space so that we can get it in context here. So flipping a coin. When you flip a coin, what are your options? What can result? And let's just go non-Twilight Zone here.
I was going to say.
Non-Twilight Zone, you can get heads, you can get tails. What about tossing a 6-sided die? What's my sample space? What are my options? I can get a 1, a 2, a 3, a 4, a 5, and a 6. Notice I'm using the brackets because just like in range and domain, we're talking about all the things that are included. What about this? You're taking an antibiotic for a sore throat. So what are the 2 possible outcomes?
2. Sick or not.
Okay, I heard it. Works or it doesn't. So a possible outcome is sore throat, remaining, or just stay sore throat. And then healed or no sore throat.
Vaccines don't do anything.
Or you could say that it works here for the no sore throat. It doesn't work over there. Continuing our talk here, if you chose an integer from 1 to 100, you have 1, 2. Feel free to list all the numbers or just do ... ellipsis, like there. So 1, 2, skip a few, 99, 100.
Not 2 dots, not 4, but 3.
And there we have it. Okay, so let's walk through our first example and then have you practice a little bit. Example 1, we have two 6-sided dice. One of them is red and one is green. So there's a complete difference. One's red, one's green, so we can clearly see which one is which. They're thrown, and both numbers are recorded. So we're going to list all the possible outcomes and how many outcomes are in the sample space. So if we just start making a list, and let's assume we're going with the red first for no particular reason. So it could be 1, and then the green would be 1. So that would be a 1, 1. Well, what else could we do? A 1, 2. What else could we do? A 1, 3. Well, notice that this list is going to get quite large because I have to keep going down the list of ones. When I'm done with that, I have to go to the list of 2s, like so. Then 2, 2, etc. ... And in the end, what do we get? We have 6, 5, and 6 -6. So 6 options on the red, 6 options on the green, 6 options on the red, 6 options on the green, total of 36 possible outcomes. Your turn on this one. What I would like you to list on example 2 is that you're going to list all the possible outcomes. You don't need to list the repeats. So you're going to list all the sample space. And second, you're going to count them up. How many options are in the sample space? So as we look at this box here, with 30 purple clips, 30 blue clips, and 25 yellow clips, these are the only 6 options that you have. Now, it's probably more frequent. Some of these are more frequent than others that can occur, but these are the only 6 potential options. You're not going to extract a black one, say. And the reason, again, is that we assume that what they say right here knows everything. Like your little brother didn't come in and sneak in a black clip, right? This is what's in the clip. There's no other option. Excuse me, this is what's in the pink box. There's nothing else. So you have to go with what it says, and don't read into it, and don't say things like, well, aliens could have abducted me, and I could have been hypnotized and put something else in. Whatever. We're just going with what we see there. All right, so how many possible outcomes are there in the sample space? And the answer, of course, is there are 6 possible outcomes. When 2 dice are thrown, a casino goer, that is, one who goes to a casino, might be trying to get a sum of 7, because that's a big deal when people are throwing dice. Or when they're flipping a coin twice, a person might want tails twice for whatever reason. So each of these is called an event because it happens. But not necessarily because it happens, also because it might pretend to happen. So the event of getting, rolling a 7, or, the sum is 7, or rolling a 6 and a 1, something like that, etc. Of flipping coins and getting tails twice. So, if a red die and a green die are tossed, like in our previous example, we're going to list all the possible events and outcomes below. So, the outcomes of tossing a double. So, what are the outcomes for double? Well, what do we have? We have doubles. We have a 1 and a 1, 2 and a 2. And as you can see, we can just keep going here. 4, 4. If you wanted to put dot, 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 I'm already committed, so I'm going all the way. But you can put dot, 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 and end at 6, 6. But only 2 6s. We're not crazy. All right, so this next one, tossing a sum of 10, we see 5, 5 and 6, 4, but of course 4, 6. The reason why these switch is because in one of these, we have a blue and the other one's a red. So this one's the blue and this one's the red. So that's why we can switch those around. My assumption, and I'll double check this, but if they were the same color, both were black dye each, I don't know, then my guess is this would not be one of them, because we couldn't differentiate the colors. The only thing you would say is the one on the left or the one on the right or something like that. Okay, tossing a 3 on the red die. Well, tossing a 3 on the red die, and notice that the red die is listed first up here. So if you just list it first here, just because it's listed first, but ultimately it doesn't matter. Ultimately, it depends on what you call it, and as long as you're consistent. So this is 3, 1. That is the blue is the green is a 1. So a 3, 2, and then a 3, 3, and continuing on until we get to 3, 6. 6. All right, and sum of 1. Trying to get a sum of 1. Never. This right here, by the way, is called, and I'm going to put brackets around it, it's called the null set. And I just want to point out to you that this does not mean 0. In the sense of, like, it can sometimes mean 0. It just means blank. It means blank. And so when we talk about probability of rolling dice that sum to 1, the probability would be 0. But there contains nothing in the set. So it doesn't contain a 0. What it does is contain nothing.
It's not even 0.
Not even 0. Because often 0 can represent something that is on, that represents an actual number. And here just represents a blank slate. All right, take a moment real quick with your partner. Where would you place these terms on this spectrum here? Certain, equally likely, impossible, unlikely, and likely on this spectrum of 0 to 1. So let's see here. Impossible is down here, of course. The impossible of winning the lottery if you never play it. That's up here. Certain, death and taxes are certain. Right here. I'm certain that I exist. The reason I'm certain of that is because I think, as Pascal says, I think, therefore I am. I am not certain that you exist. Descartes, thank you. I am not certain that you exist, although I believe it probably to 99.9% certain that you exist.
I would put you're certain you exist in it too, because
I know
how are you certain?
If the probability of an event E, of course we just use E for that and we substitute that in, whatever it is 25%. Shh. We could also say, 1 over 4. We can say 0.25. We can say 2 to 8. So anytime we have an equivalent mathematical expression, those all mean the same thing. It is unlikely to occur. And these are some possible equivalent ways to write it. We would also say that it is unlikely. And of course, it's on a spectrum, so impossible is 0, but pretty darn impossible would be anything, under 10%. Well, not under 10%, pretty close to 0. But unlikely would be, anything in this region here. Equally likely is almost an exact thing. So likely would be something around here, certain, high, up there.
Is there any?
All right, just to keep job security here, I put this down. So let E be an event in a finite sample space S. So let N of E and N of S be the numbers of the elements in E and S, respectively. So this is the number of events, favorable events, and this is the number of possible events that can occur in my sample space. If each outcome is equally likely, so there's no bias, there isn't someone orchestrating events, then the probability that E occurs is called the probability of E and is denoted P of E. And is given by this. P of E is equal to N of E over N of ES. So that's the number of outcomes in the event, number of outcomes in the sample space. And maybe back in 6th grade, you probably look at it like this: the number of favorable options over the number of possible options. What you want over what you can get. What you want over what you can get. All right, so let's just see here. In the 2 dice situation from previously, we're going to find the following. What's the probability of getting doubles? The probability of getting doubles. Well, in order for us to answer that question, we have to know how many doubles, number of doubles, over the sample space. The number in the sample space. Now, we already know the number in the sample space. We counted it previously to be 36. From 1, 1 all the way to 6, 6. And the number of doubles, all we have to do is go count that. And when we count up our doubles, 1, 1, 2, 2, 3, 3, etc., there are 6. So in this case, the probability of getting doubles is just 1/6. You can leave it as a fraction. You can also write it as a decimal or a percent. So 16.7% approximately. Notice the approximate there. So notice this, that getting a sum of 10 is 1 out of 12 options. So you expect that if you rolled the dice 12, you would get it once. That's your expectation. And if it didn't happen, you would expect within a few you should get a sum of 10. Now this is theoretical probability. Experimental probability is when you actually do it, and that one time gives you some numbers. Notice here, because this one originally is 6 over 36, and this one's 3 over 36, you're twice as likely to get doubles as you are to get a sum of 10. You are 2 times more likely to get this than this one here. All right, a sum of 1, 0. In this case, we could argue that getting a sum of 1 is impossible. Oh, but what if I drop my dice, one of my die? Then it's no longer a sum, and it's no longer part of a question. What about this? The sum of not 10. So if up here there are 3 sum of 10s, that means there are 33 not summing to 10. So in this case, 33 over 36, which now becomes 11 over 12. Notice here how they're related. I don't want to say they're complementary, but they're like, I forget the word, but inverse-ish. They sum to 1 here. So it's kind of like supplementary, but with 1. An experiment consists of tossing 2 fair coins. And by the way, just so that we know what the term means, fair means that it's unbiased. Fair means unbiased, that it's equally likely outcomes. So a fair coin, a fair dice, or a pair of dice. These are all fair. We assume that one doesn't weigh more than the other, or there's not weird things going on here. And counting the number of heads that are that show up. So consider the events 1 head in all, 2 heads in all, and 0 heads that show up. Are these events equally likely? So let's see here. One way to do this, to visualize it, is just to start thinking about my options. Well, what if on my first roll, or toss, the first one, my option was heads on top. And then the other option is that I have heads on top. So that means it was heads, heads. Now, my second option is the first one was heads, the second one is tails. So I get heads, tails. Now, continuing this tree diagram, my first one could have been tails and tails. So then that's tails, tails. Or tails, then heads. So that would be tails, heads. So when we count these ones up, consider the events 1 head in all. Well, look, 1 head in all is either this one or this one. So, is it easy? Can we differentiate which coin is which? Well, not necessarily if they're the exact same coin. They're both quarters or something. So I don't know if this one's the first one or this one's the second one. but I know that it can show up twice. So that means my option here, the probability of exactly one head showing up is 2 over 4. So it's a 1/2, a 50%. It's equally likely to get only one heads. Okay, so what about the other one? What's the probability of getting 2 heads? In this case here, I see that it's exactly only shows up once out of my 4. So I have a 1/4 chance of that happening. And lastly here, what about the probability of getting 2 T's? 2 tails, and in this case would be 1 over 4 also. So, are these events equally likely? And the answer is no, they're not all equally likely, but these two are equally likely. So I have twice the chance of getting just exactly one head there, as opposed to flipping 2 heads and 2 tails. So these are the steps over here. I made my tree diagram. I counted the possible outcomes. Here of them, 2 of these here. And then I computed the probabilities there, etc.